Homework 5, problem 4. Find the vector potential A for a wire carrying a constant current density, where inside the wire you have a constant current density A naught. So for S less than A, you have that. For outside the wire, it's 0. The trick here that we're going to use is we're going to use the definition of A. The definition of A, of course, is that the magnetic field is given by the curl of A. Now, that means in order to find A, I'm going to first have to find B. And so that'll be step 1, we'll be finding B. Well, finding B, we know how to do that. We're going to use Ampere's law. And so for Ampere's law, all we're going to do is we're going to draw a circular Amperian circuit around our smooth thingy here. And so this would be it. I'm going to go in that direction. And Ampere's law is written down as the path integral over loop dl dot 1 over mu naught b is equal to the amount d2x n hat dot j, the amount that goes through this circuit. Here we can make the argument through symmetry that B will be in this phi hat in this azimuthal direction alone, and dl is also in the azimuthal direction alone. And so the left-hand side of this can be written as 2 pi s, so let's make the size of our Amperian circuit here s, 2 pi s over mu naught times constant b naught, not constant, b as a function of s in the phi direction. Okay, and this should be equal to, and now we have a piecewise. Okay, if we have this is the total current that flows through. If my circle is smaller than that, it's just going to be J naught times the area of the circle, which will be pi s squared times J naught. And if our circle is bigger than that, it's going to be pi a squared times J naught. And this is for s less than A and for s greater than A. And so that tells us what B is. B is circling, looping around in this direction, so this is going to give B in the end is going to be looping around in this direction. It is going to be, the pi's are going to cancel. I'm going to get mu naught, J naught, over 2 times s for s less than A, and I'm going to get mu naught, J naught, A squared over 2s phi hat for s greater than A. Okay. And so that tells us where the magnetic field is. The magnetic field is swirling around the current, and yeah, that's it. So we're going to have little magnetic field lines, right, that look like this. And so these green lines are our magnetic field lines. Now the trick that I told you before is I'm going to use the definition of the magnetic field, or of the vector potential here, using the magnetic field to find A. And I'm going to do that, and I'm just going to apply the same idea. The fundamental theorem, when applied to a curl, is going to give us that the integral dl dot A, that's the fundamental theorem applied to that side, is going to equal then the integral d2x n hat dot b. And so I have to figure out what type of Amperian loop that I want to draw here. Well, the Amperian loop that I'm going to want to draw is going to be a loop that looks like this. Okay? And so it's going to be pierced through by the magnetic field at these points here. from the center of the wire out to this inner edge, we're going to call it A. From the center of the wire out to the outer edge, we're going to call that loop B, and we're going to say the loop has a height capital L. Through the symmetry of this problem, I can see that the vector potential is going to have to point in the z direction, positive or negative z direction, probably the positive z direction. I could also get that because I have an expression for the vector potential in terms of current density, and they're related component by component. And so that expression, if we want to write it down, would be that, what is this? A sub z is going to be the integral d3x of j sub z over x prime, j sub z of r minus r prime, right? And so if my j is in the z direction, my a is going to be in the z direction as well. So I've got two kind of indications from the symmetry of the problem. With that statement, I'm probably going to have it only in the z direction, and from one of our expressions for the vector potential, we're going to have that. Anyways, looking at this, since it's only in the z direction, I only need to worry about these two loops. So I'm going to go ahead, I'm going to make this loop around like that. That means this is going to, my n hats is actually going to point into the negative phi direction. So my n hat is going to be in the minus phi hat direction. And so I just have to actually evaluate this. For this one, it's going to be constant along that loop. It's going to be 0 along here. So this is going to be a sub z evaluated as a distance b times L minus L times a sub z evaluated as a distance a. And this should be equal to now the current that flows through here. But I have this here, this is phi, this n hat is phi hat, or is minus phi hat, so I'm going to get a minus here. And so this is going to be L, and then times the integral from a to b of ds, and then I'm just going to have what this expression is, right? Where here I have to be a little bit careful. I've messed up. I've called the size of this A, and I've called this one A. Let's call the size of this A naught. Not. Okay. So going through, that means I'm just going to have to plug in this value of b, and so this is this expression here. This is mu naught j naught over 2s, or a mu naught j naught over 2 a naught squared over s. In order to uniquely find this, I have to define some point to be a equals 0. The most convenient point is obviously going to be at the center. Okay, so if little a is equal to 0, or let's restate this. Let az of 0 equal 0. Okay, I have freedom here. This is only defined in terms of a gradient, or in terms of a derivative operator, so I can move it up and down by a constant, and so I can set any point equal to 0. So I'm going to let the point along the center of my line be 0, and the L's are going to cancel, and so that means that from this expression here, az as a function of s is going to be equal to the integral from, or minus, I'm going to give this minus, the integral from 0 to s ds prime of b phi as a function of s prime. And so this is the expression that we have to evaluate. The integral of for s less than a, we only evaluate this one, and so this a is going to be equal to, in this case, mu naught j naught over 4 s squared for s less than a, and for s greater than a minus. For s greater than a, we're going to get the integral of 1 over s is log of s, and so this is going to be mu naught j over 2 log of s over a minus mu naught j naught over 4a squared, and this is for s greater than a. And so that's our expression for finding a. And all we're doing is we're using basically the same idea of Ampere's law. We're just applying it to that equation instead of the Maxwell equation, which I never wrote down the Maxwell equation. The Maxwell equation, of course, is del cross 1 over mu naught b is equal to j. And so this gives that, this gives that, right? So this gives that, and then this exact same structure will give that same structure there. Finally, I might want to plot what this looks like in this case, and so going through and doing that plot, we're going to call this the AZ, and we're going to call this S. We're going to make this point right here a naught. Let's make this minus AZ because I didn't give enough room to plot in the negative sense. This starts off as a power. It's going to grow like a power until we get to A. It's going to grow like this is proportional to S squared, right? So it's going to grow like a parabola. And then at this point, it turns logarithmic, and so it's going to grow like a logarithm at this point. Okay, and this is proportional to log of S over A. And that's it.